Thank you everyone once again for being here today. We have a Greener Curriculum Showcase series on the topic of bringing real-world industrial skills to the classroom, teaching life cycle analysis and techno-economic assessment, also known as TEA, by the dearest Dr. Julian Silverman. You'll get to hear a lot about what he's done on the topic, and I hope that you will leave this meeting empowered enough to start doing a little bit of this in your curriculum if you're already not doing that. And so please use the space to ask questions and be very empowered to, bring all the challenges you have incorporating some of these concepts into your classrooms. So there will be live transcript. You can enable that by clicking the CC button at the bottom of your screen. And also the recording from today's session will be made available to you after the workshop. And just a reminder, everybody is here to learn, everybody is here to contribute. And so please make sure that you let everybody you are interacting with feel welcome and included. Treat everyone with respect because we are all here to help learn and promote green chemistry education. Okay, so this is a tentative workshop schedule. So Julian is gonna give you a broad overview on those two concepts, life cycle analysis and techno-economic assessment, as well as green chemistry principles. And then he's gonna delve a bit deeper into some of the activities in the module that he developed around these two concepts. And then there's gonna be, as Julian said, there's gonna be a lot of time for contributions and questions and stuff like that. So just a reminder, bring your questions, feel empowered to bring your ideas to the table today. And this module that Julian is going to talk to us about is actually part of a soy chemistry curriculum that was developed by Beyond Benign with funding from the United Soybean Board. And so we want to take this moment to acknowledge their support for making this possible. And we also have a lot of other funders who help us to do the work that we do at Beyond Benign, and would also like to say thank you to all of them for their support over the years. Okay, and last and not the least for me, we do have a workbook that sort of gives a quick summary of some of the things you'll be hearing today. And so you can use the QR code to get access to that if you did not receive it from me through my email yesterday. And I'll also put the link in the chat briefly. And with that, I would like to introduce Dr. Julian Silverman, who is an assistant professor at the Fashion Institute of Technology in New York, to share with us what he's got on the topic today. Thank you.
Thank you, Monica. First off, it's a pleasure to be here. Something we'll learn about both life cycle assessments and techno-economic assessments is they are never done alone. So I actually wanted to start with some of my acknowledgments, not only Beyond Benign, but my colleagues and researchers like Jane and Michael that you see here, along with Chris and some others from Omnitech. They really helped bring both an industry perspective to some of the college and high school level chemistry that we do. So you'll see a lot of their work embedded in what we'll see here. So again, there's kind of different ways to work with this workshop today. If you are already a little bit aware of life cycle assessments and these kinds of methods, you're welcome to really dig into the materials. But if you're relatively new to LCA, I would say feel free to sit back and listen, ask questions as we go. But we're going to start with kind of a broad introduction to these different topics. So today, as I said, we're going to explore two related types of assessments. One thing I will note, because we have some pedagogical assessment experts in the crowd today, is that this is a little different than making like a final exam. This, if anything, would be a little bit more of the methods to crunch numbers and really figure out if things are more sustainable. And so we'll look at this from two perspectives: the techno-economic, which no surprise is focused primarily on money, but also whether things are efficient. And then also the life cycle assessments, which are a little bit more popular and look very broadly at environmental considerations. But it's no surprise that these not only overlap, often in industry these days, they use both really to figure out if something is scalable, if something is good for the environment. And the way we're going to explore this is by looking at soy products. So that is a very broad class of chemicals and materials. But as you know, our partner with this is the US Soy Board. And I will tell you that as a chemist and educator, I go to the Green Chemistry and Engineering Conference almost every year. And for many years, I would always walk by the US Soy Board booth that they have. I remember they were always giving out chapsticks and other things made with soybean oil. Now that I work at an institution that really isn't a scientific institution, but looks at making consumer products, it's no surprise that soy is a very valuable feedstock. So thinking about not only taking, food chemicals, but we'll also talk about using waste chemicals, really bringing in these green principles. If you're in the United States, but also in different areas across the world, soy is a very valuable resource. And so we'll explore its different uses. With that said, this is really focused on curriculum development and bringing, again, methods they use in industry into your classroom to make it more relevant for students. So you may have more soy questions after than you did when you came in, but that's going to be a good thing. And so, as we talked about today, we're going to do this in three acts. The first act is just a broad overview looking at sustainable principles and goals. We'll do some activities where you will talk a little bit about really why you're here in this workshop, right? Why you care about sustainability, but then also how you think this might be adaptable to your classrooms. And then we will do a mini TEA together. So, the Techno-Economic Assessment will crunch some numbers. You are more than welcome to sit back, but if you have a calculator or a phone on hand, you are definitely invited to do relatively simple math. I'll do some math for you to begin with, but towards the end of the first hour, we'll have some calculations to do to see if an activity you could do in your lab is actually more economic than what's on the market. And so at the very end, I'll do a brief workshop that I've given before focused on really writing learning objectives. And so this is going to be the way that you could take the broad diversity of ideas we'll talk about and make them actionable for your courses. There are many different ways to design your courses or curricular materials. I always use learning objectives because they are clear, not only for me, but for my students as well. And so, without further ado, I'd like to know a little bit more about you. And actually, Monica, I'm going to ask you to launch the polls if you can, so that I don't have to come out of here. But I'm going to ask you just three different questions to get a sense of where you're coming from, what your interest is in sustainability, and then, maybe a little bit about how much you know about these different types of assessments and methods. So the first question is very broad. This is more as the everyday person, maybe not as the educator. But if you hear sustainable for a product or a process, what comes to mind? Is it more about what it's made from? Is it how it's manufactured? Is it how it's used and maybe disposed of? Or maybe you don't think about this much. Maybe you just take it at face value. Our second question is now about really comparing different products. This is pretty common with life cycle assessments where you'll have like a benchmark you're comparing to. For the second one, what would mostly influence a company to make decisions regarding a new or different product? Your company is going to care more about environmental impacts, the cost of production, getting something quickly to market, or perhaps how marketable it is. I'm sure we've all seen consumer products that don't work but sell very well. I think about you were marketing Labubus, you probably wanted them out there very quickly, right? They're not as popular now a couple months later. And then on the final end, how confident are you in how in determining how green a product truly is, or a product or process? You could also think of this as a single chemical from a procedure. And this is a combination of, your everyday experience as a consumer, and then, your background as a scientist or educator. I'll be honest, even though I've been doing green chemistry work for over 10 years, it's difficult. Even I stand in the aisles of the supermarkets, kind of looking at two different products, figuring out what might be best. And it's no surprise that the real answer is it depends, right? It depends on who you are, where you are. And so that's really what we're going to find today is that the beauty of life cycle assessment is not that it tells you exactly what's best, but rather that it gives you a different perspective to evaluate options. So again, more questions when you leave than when you came. But I'll be honest, that's what I do with my students. I don't try to give them answers. I try to have them ask better questions. And so I can see that we have some good responses on our questions. And so I'm going to go ahead and share our results as well. So it's no surprise that I would say for our first question, it's really a combination of all three things, right? We'll find that where it comes from, how it's made, and where it goes is essentially the life cycle of a product. So it's good that we're thinking about all these different things. My guess is based on your backgrounds, maybe if you're more of a chemist, you think about the ingredients. If you're more of an engineer, maybe it's more about manufacturing. All of my students are more marketing and business students, so they're really hyper focused on, right, how it's used and how it's marketed. And so we'll find again that we want to think about these different things together. At the same time, we will find that there is not only a green set of principles and rules that we want to follow, but what I will call our golden rule, which is that for the most part, cost is going to drive a lot of economic and industrial decisions. So we'll cover that a little bit later. And it's, not surprising to see that we have some people very confident in looking at greener products and some that aren't sure at all. Of course, the other challenge is things change very quickly, right? The kinds of ingredients we use, what is sustainable. Let me know in the chat if anybody's been following this microplastics debate this week, right? There might be some new analytical data about how much we're ingesting. Again, things are changing really every minute. So with that said, I do want to introduce myself just a very little bit, and the way I chose to do this today is by sharing some of the resources that I've developed and have on the green chemistry teaching and learning community. So my hope is that you're all either participants or active users of the GCTLC. Even though I'm at FIT, I teach really a broad variety of students, and I get to do some forensic chemistry and some cosmetic chemistry. So you can see here I have activities really for the undergraduate labs, focused on a little bit of alchemy and the history of chemistry. The middle one is my absolute favorite activity we do every year, where students forage oak leaves from around Central Park, and then we dye fabrics with them. So getting really hands-on and in the lab. And then more recently, with Beyond Benign, I've been working on incorporating toxicology into our class, which is again very relevant for life cycle assessment. Often you're interested in how hazardous a chemical or material can be. And so here with my colleague Saskia, we developed a very simple activity, all based on really open access resources. So one of the goals of Beyond Benign is to not have you pay a penny. In fact, they're very good at providing funding for opportunities. And so know that you can access these today. But one of the things I'll say early on is we don't want you to just plunk them down into your courses. You're more than welcome to do that. But more than anything, we want you to be able to adapt them for what you and your students need. So that's going to become the focus of the latter part. And I want to thank not only my current colleagues who helped me develop these, but some of the colleagues on the call were in review. This is similar to submitting a journal article in that there is a peer review process. But especially for educators that are very busy, it doesn't take nearly as long. So I would say about half the amount of time for a journal article at times in terms of reviewing. And so if you have an activity you love to use with your students, feel free considering submitting that to the GCTLC. And so, where I really want to begin is why we're here. And we talked a little bit about your interests in sustainability. But I would love if you could type into the chat a sustainable development goal that you see on this page that resonates with you. And I'll be honest, I'm not going to go through all 17 of these today. We don't have the time for that. My hope is that you already have a little bit of a passion or interest for one of these topics. I always tell my students that when I first started in green chemistry, I felt like I needed to do all of these myself, like to do 17 different things. That's a pretty grad student approach. But what I've really realized is that if we individually target different goals, right, there's more than 17 people on this call, then we'd be able to help achieve really great things. So created by the United Nations, this is a global effort to address a variety of different economic, social, and environmental perspectives. And I can see, not surprised to see some educators focused on quality education. We also have things like clean water and sanitation is very important. And so it's no surprise that based on where you're from and your personal interests, you're going to have perhaps, a closer connection to the different goals that you see here. One of the things I always do with my students is not only have them identify the ones that they really love and focus on, but also the ones maybe they're less comfortable with. I'll tell you that I am really an educator at heart, but I spent some time working in an engineering department where they were really focused on both innovation and industry in a way that was new to me. And so being aware of what you have strengths for is just as important as realizing what maybe is more of a challenge for you. So now let me flip the script a little bit and ask, what's something on here that you know to be important, but maybe is a little bit out of your wheelhouse? What's something you'd like more experience with, or maybe to find a collaborator to help you with? I'll say that at the Fashion Institute, we make a lot of designs and actual consumer products. And so number 12 is something that I've always wanted to become more invested in, but it's challenging to do on your own. I can see we're interested, no surprise in our current times, and economic growth. I can see that on here. Peace, justice, and strong institutions, very relevant. And then there's some that, can look different in different places. Like number 11, as Emily's pointing out, sustainable cities should look different, right? So we can take good ideas from different places and adapt them to where we are. So take a moment again to look at these because we're going to do a short activity in a moment where you're actually going to link these to different principles. So even beyond the ones that you know and love, we're going to start to explore how these will show up in life cycle and techno-economic assessments. And so the way we'll do this is by re-exploring some of the green chemistry principles. So there are many different ways to be sustainable, as you can see on the left here. But I would argue that underneath these everyday actions and the actions you might do in your lab, are the principles behind them. And so I'm not going to ask you to point out some of the actions on the left that you do. My guess is some of you are already printing less paper or turning off the lights when you leave the room. Instead, what I would love to see is you connect an action and a principle. So again, I'm not going to go through all 12 of these principles here. I'm going to kind of lean into the ones you're maybe familiar with. There are some chemistry standards like catalysis, number 9, right? Using an agent that isn't broken down but sort of facilitates a reaction. Number 2, atom economy is focused in some ways on efficiency, making sure you use everything that's put into a reaction or is become part of the process or product. And so take a moment and from an action on the left, see if you can pair it with a green principle on the right. One of them that I always do is bringing a reusable bag. That's something I've become really good at in the last couple of years shopping in New York City. And I would say that you could touch on a variety of principles, but the one that's most closely is probably waste prevention, right? Rather than getting a plastic bag and then throwing that out, I have a reusable bag. And so this is your first, I would say, challenging question. See if you can link one of our everyday actions on the left with a green principle on the right. Think the challenge here in part is we often think of the green principles as being very chemistry focused. And even though there's chemical elements in a sense to these everyday actions, the principles here are the same. And so what we're going to find shortly is that even though we think of the principles of green chemistry as in some ways like a checklist of 12 things we want to do, these fundamental principles of efficiency, of safety are going to begin to appear in these assessments that we do. And so Stephen here is talking about eliminating single-use plastics and waste prevention, another very important one. I laugh. I feel like reusable water bottles are like everywhere now, like everyone has them on their person at all times. It's no surprise too that we're highlighting waste prevention in several different activities. These are not necessarily hierarchical, but number one, waste prevention will become one of the most important principles we'll see. And so with that said, I can see you're starting to link these different kind of actions and principles. And so these are the things we really want our students to be doing, right? We don't want them just blindly eating less meat because they were told, right? We want them really understanding that eating less meat can be related to energy efficiency, right? Feeding people with crops rather than animals, for example. And so as the challenges change over time, whether or not microplastics are as bad as we thought, for example, we'll begin to see how we can incorporate these ideas. And so I'd like you to take a moment to inch your way into the world of soy chemistry. Now, there's obviously a lot of information on this page, but on the left, we have our sustainable development goals. In the middle, we have our green chemistry principles. And on the right-hand side, I also have for you the 12 principles of green engineering, which are very similar to the green chemistry principles, but again, kind of expand the context we're looking at. Both LCAs and TEAs are really I don't want to say engineering focused, but they draw a lot from the world of engineering. And so these might be completely new to you, but we'll start to think about where they might show up or how we can incorporate them. Moving forward, let's take a moment to look at some of the benefits of soy chemistry. For example, soy plant protein can replace animal protein, right, for foods, things like that. Lecithin emulsifiers can be used in formulations in making cosmetic or consumer products. And carbohydrates from soy, which are a minor component, are biodegradable. You might use them for something like packaging for consumer products instead of something like plastic. And so the second challenging question I'm going to ask you is kind of a riff on what we just did. From these three ideas, can you link them to an SDG and a green chemistry principle or an engineering principle? So you're going to take one of these three elements at the bottom of the screen and just suggest which of the SDGs or green chemistry principles they relate to. I'll do the top one for you. But again, I would argue that using plant protein versus animal protein could be done for health and well-being, right? There's some people who maybe don't eat animals for ethical or maybe even religious reasons. And so to be healthy and well, you need protein. Soy can offer that as an option. That's the sustainable development goal. Now, on the other end, as I said, plant proteins are often more energy efficient than animal proteins, right? It takes a whole field of wheat to feed an animal, and then that animal doesn't feed as many people as that field of wheat. So thinking about, right, how much sunlight you absorb and the trophic levels, all that kind of fancy science, we see here that, right, we can link this energy efficiency, principle number 6, over to something like good health and well-being. And the reason we do this is because this is not only how we're going to motivate our students, but this is how we're going to interpret what comes out of techno-economic and life cycle assessments, right? We know that our goals are to make things better, more efficient, but we need to figure out how to do that. And the how is really going to be the green principles. And so in this case, this is definitely open to interpretation, but I would say that using bio-based or natural emulsifiers is more innovative, perhaps, than using petroleum-derived alternatives, and it could lead to safer chemistry. Often, not always, some natural or bio-based chemicals can be safer for skin, for example, than some others. Not always the case. And then on the other end, using biodegradable or bio-based materials can be better for life on land, right? Not polluting with plastics, and then also always better from a renewables perspective. So know that all of these ideas are going to fit into these life cycle and techno-economic assessments. And so let's start introducing some of the resources that we're going to use. Now, I am still on break. We don't go back until the end of January. And so I apologize a little. We gave you a 20-page homework to do before today. We gave it to you one day ago. But on the left is an image or screenshot of that homework assignment that you were given. And on the right-hand side is the document that you would have assessed if you had gone through the homework. And really what it was doing was looking at a brief where they turned soy chemicals into functional surfactants for soaps and different products. But really, what the homework had you do, as an example of the resources we'll talk about today, are what we just did, the activity we did, in about 5 to 10 minutes. While this would be about an hour-long activity the students could be doing at home, it serves as a perfect introduction to sustainable development goals, green chemistry principles, even engineering principles, if that's part of your coursework. And so, we don't need to do this in full length here, but, which of these soy chemistry topics relates to which of these different principles? And so this was the first step in the modules that we began to develop. Before you get into the heavy topics of calculating energy efficiency and cost savings, we want to make sure that students and educators really appreciate why we're doing what we're doing. And so even introducing topics related to soy chemistry, you can begin a really big discussion about, right, sustainable ideas, how we reach them, these green principles. And so, for example, in this brief that you would have gone through talking about surfactants, part of the innovation was that it was a novel manufacturing process. And so here you can link the SDGs. We can also start to think again about, preventing pollution, for example, by using safer surfactants that have a lower dermal toxicity. And so by relating different ideas and having students identify which these are, it's going to be more meaningful when you get the numbers out of your TEAs and LCAs. And so if you didn't get a chance, you're more than welcome to do this homework anytime you want. But I would say that as a very easy introduction to green chemistry principles, just having students identify from a relevant journal article or topic or content is a great way to have them start to think not only if something is green, but how and why it's actually more sustainable. And that's really the ultimate goal of an LCA, not just to make something better, but to understand why. And so I'll tell you personally, as an educator, I work with a couple of different tools and methods. More than anything, Bloom's taxonomy is really about how students grow throughout a course or an assignment, even, right? Going from very basic things like remembering or recalling information, memorization, up to the highest level where you're really creating complex ideas, maybe suggesting, right, which product is safer or more sustainable. And so know that in all of our modules and all of the activities that I do, generally, you're going to work through all six of these different steps of the taxonomy along the way, and it will get more challenging as you go. And so you, of course, know your students better than me. But in this case, um, if you have the time or the opportunity to do really complex stuff, that's really where I would see TEAs and LCAs fitting in. With that said, as they enter the workforce, they're going to need to know what a life cycle assessment is if they're working for a company. So even just remembering and recalling definitions are going to be important too. So please take a moment, if you could, to throw into the chat what level of students you're working with. This could be, again, high school. You could tell me if you're working with undergraduates, and also maybe what kind of students you're working with. I generally teach non-majors. And so one of my challenges is translating some of the science for those without a background. I'll tell you, when I first came to be on Benign, I was a more traditional chemistry professor for chemists. The other thing I love to see, no surprise, is this blend of, how we can bring in real world concepts to a course, right? Like organic chemistry, which really every science student takes in some way. I also appreciate Rebecca here is mentioning professional development courses, either for educators or even just people out of school. We do a lot of graduate work at FIT focused on people entering new workforce areas. And so making them, as I like to say, dangerous in a good way, like knowledgeable about content outside of their realm can be very important. And so on the right-hand side, on top of how we do what we do with Bloom's taxonomy, there's also the methods again that we're teaching. And so on the right-hand side, you can see the waste management hierarchy, the premise that preventing waste, for example, is always better than reducing, reusing, or even recycling. Better than, of course, disposing, though that is important at some point. And so, again, you don't need to reinvent the wheel. There's only really so many actions you can do to make things greener. The question is which is going to be best for what you're doing. So thinking about, again, what level you want your students to reach, and then also what things are realistic for the setting you're in, right? We don't want to prevent the use of chemicals. That's not a reasonable or realistic concept. We want to be able to make sure that chemicals are recyclable and reusable, things like that. And so as we start to talk about LCAs and TEAs, I wanted to start with life cycle assessments because I'm a big believer that they don't have to be as complex as they seem. You could do a qualitative or number-free life cycle assessment, and I actually argue that that's pretty much what my students do when they take the subway to class, right? They think of their different options, they make a hypothesis as to which is going to be best, and then if the trip is longer or shorter than they thought, maybe they were late to class, right? Then they might choose a different option next time. Now, of course, a good life cycle assessment is very quantitative. It's going to incorporate numbers to actually prove that something is better or worse. But fundamentally, life cycle assessments have a comprehensive list of all the materials involved. Then, from an engineering standpoint, you're going to map how they come together and change. And then at the very end, in the most subjective way, you have to judge. You have to use your personal judgment in some ways to figure out which is best. And we'll see this with an example in just a moment. But the way that I explain LCAs to my non-science students is that you're looking at the product, right? The physical stuff, the process, the way it transforms, and then how these two things relate to the people, right? How the environments they're used in, the occupational considerations, or if you're just in a lab, right? If it's able to fit into your 4-hour lab session, for example. And so a traditional life cycle assessment is going to use a variety of different metrics. Its goal is going to be to look at the life cycle of a product, right? So all the way from the resources coming out of the ground, how it's processed, manufactured, sent to a store or facility, how it's used, and then also what's done after it's done. This is what we consider cradle to grave. And across all these different considerations, you're essentially calculating the different kinds of impacts. And so, among the many different metrics that they use are environmental metrics, like how much ozone is depleted by chemicals or gases that are released, how much eutrophication there might be, right? Nitrogen added to the environment from fertilizers, something like that. And these, of course, are going to be chosen based on the assessment you're interested in. If you're not using a rare earth metal, you're not going to look at if you're depleting metals. But I would argue that almost every life cycle assessment looks at something like global warming potential, right? How much CO2 or methane is released into the atmosphere. And so know that, people could do a whole PhD on life cycle assessments, but there are some good tools out there to help both educators and researchers do these on a smaller scale. One thing I will say is we developed some of those and hosted them on GCTLC. So I would say first, feel free to type that into the search bar on there later, and you'll find some good stuff. Now, one of the things I wanted to highlight is as important as environmental metrics are, life cycle assessments are often much broader than just looking at the environment. They will often look at things like, how much money could be made or costs associated with a certain process. You can also use engineering or efficiency metrics like process mass intensity. This is essentially a fancy version of the yield of a process, right? So in organic chemistry, you figure out between 0 and 100 how much product you made. Process mass intensity also looks at other things like the solvents you use, the catalysts, how much waste you make. And so these are in some ways more holistic measures. But I wanted to highlight that LCAs, while being environmentally focused, have become a little bit broader to include these different ideas. And so this is where we'll find the overlap with techno-economic assessments, because it's no surprise again that money is going to really determine what decisions get made and what products get made. And so here we have a very simple set of comparative life cycle assessments. So these are based on an aspirin synthesis that I used to do in my organic chemistry class, a very popular one. We always did it right before finals, and students laughed they were making aspirin that they might need for a headache as they're studying for finals. But what we can see here are 5 different methods. The top 2 are going to be industrial methods. The top 4 are pedagogical methods. These are ones you would do in your classroom, and the bottom one is an industrial method. The columns here represent those different metrics. So process mass intensity for efficiency, how costly it is to make a gram of product, the smog formation potential related to the release of volatile organics, and then global warming potential generally for CO2 emissions. And one of the things we see is that the greens are going to represent the best and the red with the worst. And even for a simple life cycle assessment like this, notice that no one procedure is the best. Even the bottom industrial procedure is a little bit more costly than one of the more novel microwave procedures that can be done. And so again, the great thing about a life cycle assessment as a way to evaluate a lab you're doing in class, or maybe, right, information or innovations on the market, is that it doesn't tell you which one is best. It allows you to highlight challenges in the procedures you're looking at and make improvements. And this is no better seen than if you look at the second one. Notice, for example, how relatively bad that procedure is. This was actually the one we were using in our lab, this synthesis of aspirin. It was one of the first ones that was put out in 1998. And so what we would do from a life cycle assessment like this is look at the areas where it's underperforming, like that high smog formation potential related to the solvent that was used, and think about how you could make it more environmentally benign. So what from, for example, procedure 5 could be taken and put in to your smog formation impacts, for example. The other important thing as we think about information literacy in this era where AI is everywhere and students may not know, right, the validity of the data they're looking at, is I love life cycle assessments because they highlight when things are missing. Take a moment to notice that 2 of these procedures don't have information for smog formation potential. So it'd be very difficult to figure out if this has an impact or if perhaps there's just missing data. And so in this case, um, it's just a good way to kind of also highlight what you don't know as much as providing new and more information for you. And so for here, we have to go from probably what most of us are concerned about as educators and chemists, which is the environment and the world we live in, to something we think more about in industry. So even though we can think about social, economic, and environmental from an LCA perspective, in the world of business, it's generally called ESG. So that still includes the environment and the social aspects, but you'll notice that the governance aspect here has a lot to do with finance in different ways. And so we have to admit that as much as we could come up with a really elegant transformation, it comes down to determining whether or not something is economic. And so, company could have an ESG rating, for example. And so what we're going to start to do is think about how we would do this for different kinds of procedures, not just from an environmental perspective, but including this economic aspect as well. And so, welcome to formally our soy chemistry curriculum. Based on all those introductory ideas that we talked about, I'm going to highlight really just a small portion of the different activities that are online for you as a way to incorporate all the things we just talked about into, I would say, a first or second year chemistry class without any difficulty. It would be a great idea for a senior project or capstone doing a more robust TEA. But again, if you have no experience doing your own life cycle assessments or you didn't know what a techno-economic assessment is, we're going to spend about 30 minutes really doing a deep dive. So take a moment to take a deep breath. And I guess the question I'll ask before we begin is what really what drives the decisions when you're purchasing products? So again, as a consumer, when you're at the supermarket, we call it Rain Read, the Walgreens, right? The druggist, wherever you are, and you're holding two different products, what comes to mind? This could be something you're focused on more recently, like a tighter budget in the new year, or perhaps a bigger concern, for example, I've been trying to buy products that are more refillable as of late. So before we jump into module 2B, just one of really three really robust modules, take a moment to share with me what's on your kind of shopping list day to day these days. And as you're thinking about that, I want to provide just a little bit of motivation for these next steps. I will honestly say that I'm not an engineer, and I don't do techno-economic assessments at the level you're seeing in this journal article here. I had the really interesting journey of being a research and teaching fellow in an engineering department for my postdoc, where I came with a lot of LCA knowledge, but very quickly I had to learn about the techno-economic assessments that my colleagues and collaborators were doing. And so techno-economic assessments, as you see here, can be very complex. They can include environmental aspects as well, but very much they're looking at taking really all of the data, not only of the materials, but also external factors like the cost of a material or ingredient, capital, operating costs, all these different kinds of things to really determine how viable a process or product is. And so this is what I like to call going from bench to batch, right? As chemists, often we work at very small scales, like 50 milliliters. Engineers tend to work at larger scales, maybe liters. But for things to come to market, they need to be done at pilot scale and then essentially industrial scale, right? Hundreds and hundreds of tons. And that costs a lot of money. And so before we really do even pilot scale work, we need to determine if it is economically viable. And to do that, we are going to do some techno-economic assessments. And so to teach our students about these ideas without having them really do a fundamental and robust TEA, because in all honesty, that's really upper level graduate work, we want them to become familiar with the purposes of these two techniques, how and when they are used, and then importantly, teach them just enough so they feel comfortable asking better questions. So I would not expect your students to do a full TEA. We do teach a 200 level course at FIT where students effectively do an LCA over the course of a whole semester. But in this case, don't expect them to do what we just saw on the previous page right out of the first semester. Really, we want them to be familiar and comfortable with what's going on. And so to highlight the four different resources in the module that I'll be talking about today, we have things to really touch on the different things you can do with your course. We have a lecture activity. We have a lecture discussion. We then also have a laboratory assignment and then also a homework assignment. And so number three, which you see here, was what you were given last night. And we did a little intro to this is kind of the lowest bar to entry. This was really looking at the background information about principles and sustainable development goals. I would say that this module really begins in earnest with this laboratory assignment, where students are going from the lab where they're actually making a soy-based adhesive to then doing the calculations to see whether or not it would be viable on the market. And so let me have you spoil the outcome. What do you think if you had to scale up something that you did in the teaching laboratory to an industrial scale? Do you think that that would be economically viable? I'll tell you that in my lab classes, we make a lot of inks and paints and we dye fabrics. And there's a lot of waste, right? Reagents are very expensive on the small scale. And so, surprise, surprise, one of the things we'll find is that often the laboratory work we do is not economic and efficient. But to make it so, we need to do these kinds of assessments. And today we're really going to focus on this laboratory assignment. I'll talk a little bit about what it looks like in the lab, but we'll focus on the dry lab version, so not the chemical mixing, but more so the calculations to figure out if something is economic. And yes, Rebecca's making a great point. We're going to see in just a moment. It's no surprise that buying in bulk has a big impact at Costco, but also on an industrial scale. And so we've actually already gotten through one of the three learning objectives I have for today, which is to bring in these background ideas. And so let's formally jump into how we can incorporate some soy concepts and talk about sustainability, TEA and LCA. And so these slides for the next couple are going to be the actual resources that we would use and have on GCTLC. So the beginning of the semester, you could incorporate these actual slides. But again, don't feel the need to do just that. If anything, you want to become familiar with it yourself, especially if it's a new topic or idea. Again, I was no soy expert of my own before this project, but I've learned a lot and started to incorporate soybean oil in some of our labs. But let's do it. Let's start to talk about the difference between sustainability as we think about it, and then also economic sustainability. So is something green or is it gold, and how can it be both? And so, again, I'm a big learning objectives fan. I like to include these at the beginning of almost every activity or lecture. Most importantly, these are in all of the module activities that you'll have online. So even if you don't provide these to your students, it'll be very clear what's going on in the activity. In the next couple slides, we'll have a brief introduction to two different ways to epoxidize soybean oil, essentially to take a renewable feedstock and upgrade it so it's useful for making a product. We'll talk a little bit about what's in the chat, this idea of composition and source and the material prices that are affected by how much you buy. And then, as it says on the bottom, some of the real world considerations as well. And so again, you don't need to know these things for the end of today's workshop, but these are the kinds of in-depth conversations we're having, I would say at the 1 or 200 level, depending on your students. And so a very brief introduction to soy chemistry. Soybeans are made of a variety of proteins, carbs, and oils. When pressed, you can get soybean oil, which is made of a variety of different lipids, including these unsaturated fatty acids that you see here. So those double bonds can be mildly oxygenated, or there can be a mild oxidation to get to these epoxides. And then, as you will see in the future slides, from these epoxides, you can mix them with acids to get these polymers that essentially form adhesives and glues. And so this is demonstrating a way that we can go from a bio-based material rather than petroleum and make something functional. You may know that a lot of our Elmer's glue, for example, is polyvinyl alcohol, so completely synthetic. And it also teaches a fair bit of kind of subtle chemistry. This was something that we would have learned in organic chemistry. And so it's a great kind of case study to explore the concepts that we're learning. On the bottom, you can see the comparison of two different oxidation methods. These are images from my class. We were teaching, right, strong versus weak oxidants, very important when you think about facial treatments and things like that in my cosmetics class. And so here we're going to compare and contrast something mild, like a peroxy acid to get you an epoxide, versus a strong oxidant like ozone, which might chop up your fatty acids and not give you something as usable. And so this is about as deep as we'll get today, but know that there are generally two routes to get to these epoxides using soybean oil. The commercial route is the one on the left using the hydrogen peroxide. Hydrogen peroxide, as you know, is not only a common oxidant, but it's relatively safe. In this case, it generates a different type of reaction intermediate than the alternative, which we'll talk about. And the nice thing is that both of these procedures have relatively high conversions. But you'll notice that there are differences in the product. So the viscosity of the soybean oil epoxide is different based on which method you use, right? And so there are always going to be technical considerations when we do our evaluations on top of economic ones. The alternative route, which was brought to us by Michael and Jane, they were doing this in Minnesota, I believe, to work in their polymers lab. They were using oxone, which is a solid, a combination of three different salts. And again, it provides the same product, but in this case goes through a different mechanism and route. In this case, the workup is a little bit simpler, so you might need fewer reagents. Perhaps it will be cheaper. But honestly, if you were going to compare these two, does anybody know which one is greener? Just from the information we provided, is it possible to determine which one is more environmentally friendly, which one is more economically viable? And the answer is, unless you are an expert on these topics, it's very difficult to tell, right? Even though there's more reagents for the peroxide route and the viscosity is lower for the oxone route, the reality is that you need to do the math. You need to figure out which one is more sustainable. And so the first thing we need to figure out is what's the difference between the two, right? The life cycle assessments, which we talked about, and techno-economic assessments fundamentally look at different things, but there still is room for overlap. I would say the biggest difference between the two is where your data comes from. And so again, for either of these types of assessments, you're going to need external data. I would say that for a life cycle assessment focused on the environment, you're often looking at data from safety data sheets or databases you have to purchase into. On the other end, techno-economic assessments often use data from the laboratory, right? Like how much yield there was for a process. And then it also includes things like market data, right? How much a reagent is going to cost to see if it will be environmentally and economically efficient. And so even beyond just the chemistry that I do as someone who's interested in a sustainable world, what we're seeing is that we're beginning to address more of those UN SDGs, right? Beyond just good for the environment, which is very important. We're now going to begin to incorporate the innovation and the economic growth and those things that we're interested in. And so I'd like to take a moment to quiz you. I have here for you three scenarios, and you're going to tell me which of these would require a TEA, an LCA, both, or perhaps neither. And so in each of these three situations, one of them or neither is going to be the best. And so take a moment and I'll read these out to you, and you'll tell me which one you think is most appropriate. For our first scenario, you are making a biodegradable packaging. The goal is to use some algae instead of petroleum-based food resources. You've already started a small batch in the lab, but now you need to determine if the product can be manufactured and sold at a comparable price to the things that are already out there. So this would involve looking at, right, the reactors you need, the labor costs, what it would take to scale up, whether or not there's any kind of investment required, and so that is our first scenario. I'll read through a couple of them, but I see that we have some ideas that for this first one, we generally need both. One of the things I'll challenge you to think about too is if you are limited to one, more for time and cost, if you could choose. But I appreciate that we're seeing that, right? Just because it's bio-based doesn't mean if it's green. I guess what I might add to this first scenario is imagine you're making the same product that's already out on the market. So like a bio-based polylactic acid versus a um, petroleum-based polylactic acid. So imagine that the end product has the same properties. For the second one, you're now growing mushrooms for agricultural on agricultural waste. I don't know if you've ever done this. You can actually like soak a roll of toilet paper and you sprinkle the mushroom spores on there and you can grow mushrooms. Please don't quit your jobs to do that right now, but it is possible. In this case, they're really focused on reducing emissions and landfill use, thinking about the environmental benefit compared to using an alternative commercial media like maybe logs or something like that. And so as you're thinking about number two, I will say that I agree that the first one is really focused on our TEA. Even though it is important to know the environmental impacts of any product that's on the market, if you were going to make a product that had something very similar out there, we would really be focused on really just the scale up in cost if the process is reliable. For the second one, I'm definitely agreeing with Angela and Rebecca here, right? In this case, um, it would be mostly an environmental focus here, right? So looking at imports and emissions and things like that. Now, finally, let's just say you're working in an office and you have to update some of your fluorescent lighting technology. The good news is that the company manages all the technology, right? You're really just choosing a different option. Let's imagine they are being honest and accurate about, right, the efficiency of the LEDs. You already know they have a longer lifespan. In this case, which of our two options might you do? We're always welcome to do all of them, but I would argue that in this case, considering the benefits are already widely documented, and also there shouldn't really be, presumably, any environmental or social aspects, that in this case it's just about making the best choice for your the context that you're in. I don't think you need to do math for this necessarily. With that said, there might be other impacts, right? Like fluorescent lighting is different than the incandescent lighting. That can have effects on your workplace as well. So know that this is not only challenging, but up to interpretation. And one of the cool things you can do is do an LCA on something people have only done a TEA on. And so taking a step back to look at our soy chemistry, this is from the paper that was comparing. It was essentially TEA and LCA on the soy epoxides. Notice that some of the principles they're looking at are green chemistry principles, but how they touch on different of the LCA or TEA focuses, right? So, for example, I would say that E factor and atom economy are a little bit more TEA focused. Safer solvents and safer chemistry are a little bit more LCA focused. And it's no surprise here that by highlighting the LCA or TEA, right? It kind of highlights which method is best. So in this case, if you had just done an LCA, you would probably choose the method on the left. If you just did a TEA, you might choose the method on the right. And so that's why it's so important to know which one to use and also what kind of information you're getting from both of them. Um, and I definitely agree with Rebecca in the chat talking about there are a lot of considerations with the example of bulbs specifically. I wish it were always as simple as just choosing an option on a purchasing website, but we do have to think about, yeah, exactly, some of the cost considerations as well. And so here we are again at the realization that there is more than just green principles to chemistry. And this is why we really want to partner with engineers, right? To people who value the efficiency aspect of things, but who also interface perhaps more closely at times with the business aspects of if something's commercially viable. And so this is not in any textbook that I know of, but it's something we all live by and realize, which is that even though chemistry determines what is possible in a scientific sense, economics will determine what's possible in our human world. And so again, no matter how elegant a reaction is, if it's not commercially viable, it really will not be adopted. It will not last even if it is adopted. And so in this case, we can start to compare the two different routes, thinking about some of these economic considerations. And so I know that you don't have quite an in-depth background on these two different routes, but we saw that, for example, the peroxides used more reagents. We learned that oxone, while a little bit safer, you're also going to need some more of these different reagents. And so something we'll find is that, again, there's no one best answer. The oxone route technically is safer than the hydrogen peroxide, but that is more efficient, probably the reason that it's used industrially and commercially today. And so the lab activity we did was adapting the oxone route to creating a soy-based adhesive. Even though it's not the commercially viable option, it does provide a safer alternative to be performed in the laboratory. And so some of the questions we begin to think about are, right, where does this data come from? And what costs are included in our techno-economic assessments? And so let me ask another question, which is, where do you go for your pricing data? This doesn't have to be related to chemicals specifically, Um, I will tell you that during my PhD, I tried to do a little bit of this work and found it very difficult to find prices for chemicals. One of the reasons I appreciated that we worked with US Soy and Omnitech, they were really good at getting, dollars and cents for pounds of different chemicals. But where do we think that the data really comes from? I'll tell you that for life cycle assessments, um, often they're inventories that you purchase, right? So there's a company that compiles, molecular weights and log Ps for solubility. Um, in this case, what we're going to find is that for pilot scale studies, it's generally going to come from things like published literature or perhaps industry reports, right? So there are companies out there that collect information on the cost of different reagents. Unfortunately, they're generally not freely accessible, especially for more specialty chemicals like oxone versus hydrogen peroxide. And one of the challenges, especially with AI, is that as much as it will give you a number for this, the numbers aren't going to be as accurate or precise as you might need for a calculation. It might give you a range of even just a few pennies, but that can have a big impact when it comes to determining these outputs. And so I would say the two biggest categories of what's addressed in a techno-economic assessment are what we consider the capital and ongoing costs, or these can have a couple of different names based on the sector you're in. But I like to think of the capital cost as what you need to pay before you begin, right? So like for equipment, for example, for the materials, stuff like that, versus the ongoing costs, which might be something like labor, for example, right? The energy required to run a reaction or keep the lights on when you're doing this. And so these two kind of big buckets are going to look at the big considerations we look at. Often, capital costs can be very expensive when it comes to chemistry, right? Finding facilities and reactors takes a lot of time and money. When we did this reaction in lab, the hot plate, which costs hundreds of dollars, cost a lot more than not that the student labor is paid for, but I think they get $20 an hour now in New York City. And so here we're going to start to dive into some of the numbers. I'm giving you a small gift in that I've crunched the numbers for you on these next couple slides. On the module activities on the GCTLC, you'll notice that there's a student version and an instructor version. So some of the numbers would be missing. You could calculate those together with your students in class. I will be honest with you that I teach at a fashion school where students are scared of math. And sometimes I lean into that. I make them more scared of the math than scared of the science, so they get excited for it. But the good news is almost all the math that we'll do today and that are in these techno-economic assessments is what I call Excel math. This is stuff you can be doing with multiplication and division and addition, and it can be done relatively easily. You can also set up spreadsheets and things to do much of the calculations for you so you can focus on the information and the outcomes. And that's a little bit of what we're going to do today. And so take a moment to first notice this big difference in the pricing of different chemicals, whether or not something was purchased at the lab scale or the industrial scale. So both everyday things like soybean oil, but also some of those reagents like oxone have a really big difference in price, right? They're going to be sometimes 10 times more or less expensive depending on where you're getting them from. And if any of you have ever had to purchase chemicals for the laboratory and then also searched on Amazon for how much something costs, you'd be surprised, right? How much markup there can be for small scales. And as well, hopefully that's not too big of a concern in your laboratory. But again, when starting a company, when scaling these different procedures, it can be the difference between making or breaking the viability of a process. And so from here, we get into the weeds, right? We're going to start to talk about the realities of how, if you're only making, say, 1,000 pounds of the epoxidized soybean oil versus 10,000 pounds, these factors really come into consideration. And so what you see on the screen here is that not only do the two different oxidants that we're considering, oxone versus hydrogen peroxide, have different densities, but this means that, right, a container filled with these different chemicals will weigh different amounts. You will be charged different amounts for them. But of course, because of stoichiometry, you're also going to need different amounts of these oxidants for the procedures that you're doing. If I remember correctly, you use a little bit more oxone because you have an excess compared to the peroxide, which is almost a little bit more limiting. It has to be activated before it's used. Take a moment to notice that at a small scale of only 1,000 pounds of product, the ratio is 8 to 1. But as you have the bigger scale, in this case, you need a little bit less oxone than you would need of the hydrogen peroxide. And this comes down to the sort of difference that you get with like the hot dog buns and the hot dogs, right? Some are sold in packs of 8 and some are sold in packs of 6. So at the end of the day, by scaling this, you end up needing a little bit less oxone um, in terms of the amounts that you have. But again, this is only one economic consideration that we're beginning to think about. This is just about the purchasing. We can then also begin to think about what happens when it's sitting in your storerooms, right? These are oxidants, these are hazardous chemicals. In this case, if you used all of the chemical you need for the reaction, you're also going to have leftover oxidants that need to be stored, probably need to be tested or monitored, or perhaps even disposed of. Unlike in lab, where you might just I don't know, hopefully not just wash a little bit of excess reagent down the drain. In a factory, right, you really need to think about where that 130 pounds of oxone is going to sit. And so these are things that as chemists we might not think about, but the engineers focus on quite a lot. The business people are really concerned about because for every pound of leftover chemical, this is another aspect of cost that you need to consider. Makes me very glad to be a chemist because I don't need to worry about this day to day, but it makes you realize all those little things that you're seeing along the way really begin to add up. Okay. The other piece to this is, again, really the economic concern, which is that there are different prices for purchasing different amounts of product. In this case, we can see that as we begin to crunch the numbers, the cost of the oxone route becomes really prohibitive, right? No company is going to choose a greener route if it costs almost $100,000 more than the alternative. Actually, more than that, as we can see here. And so, this is the reason we crunch the numbers, not because it diminishes the innovation that we do in the classroom or the learning that we're doing, but in this case, because it is what is going to determine what makes it to market. And so here we are thinking a little less quantitatively and a little bit more, well, I guess say qualitatively, about some of these ideas. And so, for example, some of the considerations that we've just talked about are the varying prices of inputs, the size of containers, along with how reliable your supply chain is. And with soy specific examples, this means that, right, soybean oil prices can fluctuate. I don't know if you've been listening, but they talk about that a lot, especially in the United States news, right? How much soy is produced, where it's going, how much it's going to be sold for this year. On the other end, we talk about, right, transporting soy, thinking about small versus bulk. Um, if you've ever had to, as academics often do, move across the country, right? Shipping your furniture in a container is very different than packing it into a car and driving it across the country. The important part here is that we're beginning to see all of these different life cycle considerations in our techno-economic assessments, right? Sourcing, distribution, and then also in this case, things like the quality of the chemicals we're working with. One thing to note is that these are related to these TEAs and LCAs that we're looking at. So the beauty is that as challenging as it is, TEAs allow us to include these considerations in a way that LCAs might not. They are a little more sensitive. They actually often have what's known as like a sensitivity analysis at the end, where they'll look at high and low considerations for a certain process or product. And LCAs can also have like a hotspot or sensitivity analysis, but usually, again, with a little bit more of an environmental focus. So, again, if you're teaching business students, for example, TEAs are going to be so relevant to them, it's going to be a little bit more comfortable for them to talk about than maybe something like an LCA. If you're teaching students in the humanities who are interested in the environment, maybe an LCA is a better focus. And so here we are at the end of the slides that you have online. But I did want to take it one step further. So this is an example of what the slides might look like when you present them to you. Notice that we also have further information for you to jump in. I would say some of the most important information that we provide you are access to some of that pricing data. Please don't go out and spend money on that for just an academic activity. I think that you'd be able to find good data out there. But if you're interested in doing this as like project work with students, not only will you need some of that input data, but we also have some of the resources used for traditional life cycle assessments, things like Gabby, which is what we used when I was in the engineering department. And then, of course, the foundational guidelines for life cycle assessments, the ISO, the international standards that are used. And that gets into the real nitty gritty of how those things work. relevant, I would say, again, for upper level undergraduate or graduate level work. And so now I'd like to shift to really more what this would look like in your day-to-day classroom. And so for this, we're going to take the laboratory activity designed by Michael and Jane. This is where they actually take soybean oil, epoxidize it, as we discussed, and then make an adhesive you can use as a glue. And we're going to do the dry version of the lab that we created, where you then crunch the numbers to see how economically viable it is. So I'm giving you a fair warning. There is going to be a little bit of math in a couple of minutes. And then we'll round out everything by talking about how to adapt this for your own coursework. First thing I have to do is thank my other collaborators. We did this as a pilot activity in the fall. You can see my students on the bottom left. They were, I think that's the separation part of the epoxidation, where they're right using two phases of matter to separate out the different chemicals. One of the neat spins that we added to this was we had one student group use fresh soybean oil and one student group use cooked soybean oil. Now, this is not part of the module necessarily, but just shows you how you can really take these ideas and bring them into your classroom however you'd like. I would challenge one of you to type into the chat why this is perhaps more sustainable. Why would you want to use cooked soybean oil versus fresh soybean oil when making something like consumer products? I'll tell you why you would not want to, right? It's no surprising that when you cook, food gets in there, the lipids can polymerize, maybe not in the way that you want. And so, from a green standpoint, what makes using cooked soybean oil better than fresh soybean oil? That would be for my green chemistry class. I would ask them that. Leave it to be said, we're not going to do this activity together, but we're going to use data that they generated, right? The yield, for example, to figure out if this would be commercializable. Yeah, so Emily makes a really good point. Soybean oil could be used for cooking first and then repurposed, right? So waste prevention, you're not throwing it out. And then also in this case, I always just think of food, not fuel, right? We don't want to be using food as chemicals to make glue for Labubu packaging, right? Something silly as an example. We want to be using stuff, well, we want to use food for food. So a lot of different considerations. Some of the topics that I highlighted in the lab that we did were the idea of recycling oils, which was just commented on, and then the idea of making bio-based materials like glues. Students, especially in art schools, are so used to just going and buying things and not thinking about the materials they use, right? It'd be neat to think if they could create their own. And so we ended up giving the glue we made to someone on campus who used it for a course project. Now, we'll do a couple of short activities. The first one is to sort of pick your brains, but I'll freely admit for this, you do need to have a background in organic chemistry. On the left-hand side, one of the things we can see is a process flow diagram that explores how you would make a conventional epoxy resin. Resins are similar to the glues that you might use the soybean oil for. But in this case, really what this is highlighting are the inputs, what you're doing to them, the processes, and then the outputs as they come out. And so, very briefly, I wanted to show you the procedure that we use to make our epoxidized soybean oil. You can see on the right-hand side, I've shown you the inputs, I've shown you the processes. But one of the most challenging things I try to get my students to do is to think about the outputs. Very rarely in chemistry, very rarely in even undergraduate courses, do we really focus on the waste? So, for example, can anybody highlight what the names of some of the outputs would be? These might be a little technical in a sense, but for example, if you mix a solid with water, what would be the name of that output for that oxone reagent that you're going to use? Alternatively, now we're doing some more synthetic chemistry. And so here we have the soybean oil, we're epoxidizing it. We have some hexanes or heptanes and also brine. And so what would some of the outputs be from these different processes? This is very much life cycle thinking, but also a step that you do in techno-economic assessments where you begin to think not only about, right, what goes in, how much that costs, but like what it costs to process the waste that's coming out. That's again not something we often think about as educators, but is super important both from environmental and economic standpoints. And so, for example, if we mix our oxone and water, the first output is just an oxone solution. Not very fancy. But as you may know from doing separations with organic solvents, in this case, the soybean oil will end up in the organic phase, which means that The brine, for example, is going to have the oxone with it. This is going to be one of our wastes. The magnesium sulfate, which is a drying agent, is also going to be considered waste at the end. You could be fancy and maybe dry that and reuse it if you'd like, if that's possible. But beginning to think about inputs and outputs is a way to have students think more holistically and realize all the challenging things you have to consider when, I don't know, when you're doing things at scale. And so here we are at the scariest slide that I will bring you today. And so I would challenge you to break out a phone or a calculator or open up a Google tab if you would like. But I would like to have you do what my students did. And again, these were marketing students in their junior year who take very few science and math classes, but they were able to do really the heart of a techno-economic assessment. We're going to look at one metric today. We're going to calculate what's known as the break-even point. The break-even point is the point at which you begin to make profit. It's essentially where the money coming in overtakes the expenditures that you made to buy the materials, pay for the initial labor, and things like that. So this is from the laboratory, the complementary activity we developed. I will tell you that we crunched some of the numbers for you. In this case, um, it costs $3.71 to run the reaction once from the terms of the soybean oil and the oxone and the solvents. The equipment, no surprise, is some of the most expensive stuff. Between the rotary evaporator and the hot plate and all of the glassware, that costs $1,800. Now, a realistic selling point for our bio-based adhesives is essentially 10 cents a gram, right? Glues should be very cheap, especially when you're comparing to petroleum-derived or synthetic glues. And so we are going to set an initial and very fake selling price for our adhesive at $5 a gram. This is definitely the difference between buying a Dove bar of soap from the supermarket and buying a bar of soap at a farmer's market for $10. But let's see at which point, if we sold this for $5 a gram, it would be able to come out. So I'm going to lead you through these calculations bit by bit. But if anybody is calculating along with me, the goal is going to be to get to the slot on the bottom of the second chart. How many days it would take to actually recoup your investment and begin to make money, right? Where does that break even point occur in time? And so the first thing we're going to calculate together is the variable cost per unit. And this is just going to be the ratio of the cost per batch, that $3.71. And we're going to divide that by the amount of product the students made in the lab. So that was the 1.6 grams. So you'll take your 3.7, you'll divide by your 1.6. In this case, I always like to have my students do a little bit of mental math, see if a number is reasonable. But in this case, right, it looks like it should be something roughly around $2-ish per gram. The next question, not how much, right, it costs per unit, but in this case, how much you're making on selling that is going to be the difference between the selling price and the variable cost per unit. So in this case, you might see now why we needed that $5 selling point. If it was less than the variable cost, you would never make any money, which realistically is where we are headed. But at the moment, we'll take the $5 and subtract that variable cost per unit, that around $2 amount that we just saw. Now, this is the value that you see in a lot of techno-economic assessments, this break-even point. This is going to be the number of grams that you need to make of the product to begin to make money back. And so in this case, you're going to take that fixed equipment cost, the money you've already sunk in, and you're going to, in this case, right, divide by the number that you just calculated. So this would be the $1,799 over the $5 minus that $2 amount that we saw before. From here, it's just a little bit of dimensional analysis. In this case, what are you going to do? You're going to divide that break-even point that you just calculated by the 1.6 grams. And this gets you to how many different procedures you need to do. From here, we can go from the amount of time it took. So this was a production rate that we calculated based on what our students did. It's no surprise, it's very low. They're making less than a gram every second. This is also unrealistic in that it's expecting students in my lab to be making glues for us nonstop, right? Which is not ethical. They have many other things to do. But at the very end of all of this, we can convert to the number of seconds to days and find out that it would take them 44 nonstop days just to make the money back. And so, if anything, this just hammers home the point that we've all known since we took organic chemistry back when, which is that the procedures we use in the lab are not viable from an economic standpoint. But the important part of what we've just done is that we've now highlighted where we would need to improve upon certain things. For example, the selling point to make it more economic. I will say that if you have a student who is doing, again, like a research project, this is a really fantastic way to make it more not only realistic, but also more accessible to other disciplines. So if you have a student like I often have who's presenting not at a ACS chemistry conference, but at at a school-wide presentation where there's business majors and I don't know, sports exercise majors, having a TEA to show the economic viability of the work you're doing is just a great way to make it more accessible and also potentially more realistic. Okay. Thank you for doing the hardest part of what we wanted to do today. At this stage, I'm actually going to skip this because I want to highlight the last part of what we have to do and just talk a little bit about making this realistic for you, right? As educators interested in bringing these ideas into your classroom. And the way that I always do this is with good old learning objectives. And so there are many ways to do this. And I know that there are some experts on the call who are even more knowledgeable about me than backwards design, the process of starting from learning objectives or outcomes and going to the actual activities, assignments, and things like that. But this is how I love to do it. The first idea is to have just a spark, right? Either a topic like soy or a method that you want to use, perhaps like TEA. And the first step is going to be identifying learning outcomes, right? The actual bullet points of what they're going to be able to do when they're done with this project activity course, whatever it is. The second step is determining what is mastery, right? What looks like success to you? Is that having them do a full TEA? Probably not. Is it having them discuss the relevance of a TEA? That makes a lot more sense. Regardless of what level they're at, they should be able to identify or explain how green principles relate to techno-economic and life cycle assessments. Only after these two steps, determining what they're going to do, determining what looks like they've done it well, do you then really begin to design the activities? And so the irony here, of course, is that we've brought you all these wonderful modules. And from those, you're going to have to go back a little bit, write some learning objectives, and make sure that they're suited for your course. And so for that, it's perhaps no surprise that you can essentially do a different version of a life cycle assessment. The first thing you're going to do is list out those objectives that you want done. The next thing is you're going to judge what looks like mastery, and then you're going to start to piece them together and figure out how they can work. And so there are many other great places to go for information on how to write learning objectives. Generally, I try to have them work their way up Bloom's taxonomy. So the early objectives are more about information, the middle ones are more about experimenting and playing, and then the top ones are about kind of cohering information and sending it off. But I'm also a big believer that, right, the steps of the scientific method pretty well mirror Bloom's taxonomy. So if you're doing good science, you're often creating good learning outcomes, even if they're not explicit. At the bottom here, you can see some of the ones that relate to what we've just talked about. One of my broad goals for almost all my courses are having students use chemicals in safe and sustainable ways, to use laboratory data and reference data in a meaningful way, and then, of course, to use chemistry metrics to show that things are actually more sustainable. And so what this actually looked like in my course, this is a screenshot of the actual image from the top of the lab that we did. And you can see that there were some chemistry specific ones, right? Like using a mild oxidant, but then also looking at like incorporating some of these economic metrics. One of my favorite verbs to use for learning objectives, which is really challenging for students, is to suggest or propose, right? For them to suggest which one is more green, they need to know a lot of different things. And so it's not just about throwing out random ideas, but really having them coalesce all the things they've done up to that point. And so here we can see how those four learning objectives that I wanted to incorporate in my course could be linked to some of the activities. There are definitely opportunities where you can drop something in. I would argue that almost any educator at the college level could use our homework assignment the first week of class because it's really just about green principles at a broad level. If you want to do a full TEA like we were just doing, that might take a little bit more time, involve higher order learning objectives, be perhaps a little bit later in your semester. But again, don't feel like you need to do all of this at once. There's a lot of time to build up to these different things. And to make another pitch, we're happy to help you with that. So, we at GCTLC very broadly, at Beyond Benign, and the people who are on the forums love answering questions about how to incorporate modules and ideas. So if all of this is still a little confusing to you, reach out to us. We're more than happy to share our resources, but also help you adapt them. And so the very last thing I'm going to ask you to do before you ask questions is to think about how realistically you would incorporate this into your course. So I like to do this in a reverse hypothesis. So let's first identify the outcome, something like I want my students to be able to explain economic considerations of their right laboratory procedures, capstone project, topic that we included. And then the activity that they want to do. Is this more about a discussion you're having? Is this about something they're doing by themselves? Is this about something they're doing with the literature? And so I would love if you could throw this in the chat, but you can also just think about this to yourself. If you, as the educator, do what, then what will your students be able to do? If you incorporate what element or aspect from what we've talked about today, what will that help enable for your students? And so I'm going to leave this up for a little bit, and hopefully you can add a hypothesis in the chat. But considering we only have about 5-10 minutes left, I'd love to open up the room for questions. You can definitely unmute yourself and ask, or you can throw those in the chat. And most important, thank you for your time today and sticking with us.
Do we have any questions for Julian? Okay, there are some thank yous in the chat. But just a quick, yes, Jacqueline, go.
Yeah. Oh, thank you so much. It's very interesting. Yes, thank you.
Thank you.
Yeah.
It's
So
something I will admit. Oh no, Monica, go for it.
now I was just gonna say you just received an email from me to give us your feedback on today's workshop. And so if you have not, just let me know and I will share that with you. Thank you.
Thank you.
Thank you. And I realize there's some other resources too that we'll share. I did see a question in the chat, but I just lost it. Oh, there we go.
Do you want me to read it to you?
I think I got it. Yeah. So it's about incorporating prices and residue costs, and my students could understand why we do reactions at small scales. Absolutely. One of the things I love doing is showing them procedures from the 70s or 80s and the glassware that you would use, right? The liter sized things. And then the kind of micro scale techniques that are very popular in the 90s and 2000s. Um, it's something we don't talk about as chemists a lot, right? Like the cost, even just to do things in the laboratory, but it's so important when it comes to making chemistry real. So even just thinking about how to incorporate that is a good first step.